Good afternoon, I am Mr. Ish. We are looking here at a very holistic video, the limit. We are looking here at limits from a general sense, and this video is specifically geared towards those students, college students who are at the beginning of their calculus subject or course, the semester calculus class that you might have to take. And I know for many of you, your sole priority is to get through that class, to pass it, possibly get an A. The actual conceptual and the theoretical aspects of limits is beyond your priority for now, because getting that A in the calculus class, meeting your prerequisites, is what really is on your mind. And this video is geared with all of that perspective in place. So without any nonsense, without any extra BS, we will look here at the concept of the limit from a very practical sense, because I know when you're first looking at the semester class, if you're not talking originally about a very quick preview and survey of precalculus, you will start that class with the concept of the limit. And for many of you, and for myself included when I was doing it, this concept was difficult to understand. My advice, the best way to look at this concept is to look at it through a set of questions from easy to hard, where we're evolving and steadily increasing the difficulty of those questions as we move from one to the next. Let our first question be exactly what I'll put over here. Limit as x approaches 0, we have this value here 3. Remember, what you place over here before your equal sign and after this limit expression, this right here is your function. Right here we are saying y was equal to 3. You know y equals 3 represents a horizontal line which goes right here through 0, 3. When you're looking at limits, my single best advice, if you can get a graph, that's the single best way to do limits. If you have the graph, you can read the limit off your graph. If you don't have a graph or access to a graph, maybe develop that inherent ability to generate the graphs, or then you have to utilize some of the other approaches which I will talk about in this video. To develop an answer for your limit question, you must be able to demonstrate that both a right hand limit and a left hand limit exists as x approaches a given value. Here we have an x approaching a given value, it happens to be 0. You're approaching that value from the right and you're approaching that value from the left. If that happens and that both of these values are the same, the limit will exist and you will have a good answer. So let's not digress too much here, and let's look here. Y equals 3. This is my expression here as x approaches this value right here, 0. This is my x-axis value, my domain value. You're approaching 0 here from the left, you're approaching 0 here from the right. You look up and you find where this graph intersects in terms of its output, in terms of its range value, in terms of its y value. That y value, that output, that range is your answer, and here it will always be 3 because it's a horizontal line, never going up or down, staying steadily with this flat slope being 0. It'll always be a value here of 3. No matter what your value here might be, x approaching, no matter whichever value, your answer will always be 3. This question could have very well be x approaching any other value like minus 10, 100. In that instance, your answer will again always be 3, and in all instances, the value of 3 will be right. So what have we learned here from this very most easy and basic limit question? Always approach your limits from right hand and left hand. Always try to see if both of these values are the same. And for these type of seemingly easy questions, whatever it is that you're presented normally ends up being what your answer is. Let's dial this limit question up a single notch. Limit as x approaches 0, our function is x. Limit as x approaches a, our function is x. The only reason why I'm putting a over here is this way I don't have to hypothetically start putting positive and negative values. Whenever I'm putting a over here, I mean any value other than 0, because I will always be looking at specifically a value of 0, and this will represent any other value, positive or minus. X, y equals x, that's my function. Draw it out. You don't have to draw it out, but remember we're learning this in a no nonsense mode or a way so that you can get through this subject matter here easily in your calculus class. Y equals x. As x approaches 0 from the right, as x approaches 0 from the left, you can annotate that as 0 from the right and 0 from the left right here. Your value here in terms of the output will always be 0. Why? Because this value here is 0, 0. This right here is my input value, this right here is my output value. X is input, y is output. Here you must always equal to 0 no matter what at this point. But however, when we're looking at x approaching a, we're no longer talking about this origin. A could very well have been here, a could very well have been here in terms of the x-axis value. This is my a. In terms of the x-axis value, this is my a. If you're approaching this a from the right, this a from the left, you're just looking up across and you're reading it over here. And that's exactly what you're doing. If you're approaching this minus ax value from the left and from the right, you're looking down on your graph and you're reading across. You always read across onto your y-axis values, and whatever that value is your answer. So here your answer can very well be plus or minus a, depending on what this plus or minus y value was. Remember, y equals x is the same thing as saying x equals y. Whatever is fed in is fed out, because x is equal to y and y equals x. Simple as that. Here we could have been a little bit more clear, and we could have written x approaching plus or minus a. And anyhow, your answer would be plus or minus a. This right here is still easy. Now our function has become x squared, and we're going to look at it again as x approaches 0 and x approaches plus and minus a. X squared, easy, parabola. Always like this. But look at the features of this parabola. It's a continuous function. There's no corners, there's no kinks, there's no discontinuity, there's no break. Technically, as you will learn, any function that is continuous over its entire domain, and you know this is always minus infinity to infinity, it is generally differentiable over its entire domain, meaning anywhere you could determine its derivative. But generally the better statement is if a function is able to be differentiable over its domain, then it is continuous over that domain. You will learn that in your calculus class, maybe perhaps right after you look at this limit concept and before you go into derivatives. Anyhow, as x approaches 0, x squared, again look at values here from 0 and at 0 from the right and left. You don't have to even do this. This is just you developing the habit of doing it, because for these easy functions you don't have to do this, because you could directly just put 0 into place of this, and whatever you get is your answer. And that right there is a direct substitution property of limits. I'm just abbreviating that, direct substitution property of limits. What that property of limits says, for generally rational functions which are simplified and for basic polynomial functions, you could literally just put this a value into your x. Remember, it's always limit as x approaches a. Here a just happens to be 0. So according to the direct substitution property of limits, you can eliminate this right and the left nonsense, I'll use that word nonsense, and directly substitute this a value, so long as you're dealing with a polynomial function and a rational function which has been simplified, and so long as you'll never have a situation where you'll have a negative radical which would lead to an imaginary number, and you will not end up with a situation where you have a 0 in the denominator which is undefined. If you don't have these situations, you're dealing with a simple polynomial or a rational function, just substitute your value and that exactly is your answer. Put 0 in here and your output is 0. Put plus and minus a over here and your answers are plus and minus a square. But technically I should not even say minus a square, because minus will become positive. Your answer here will always be a square. But let's look at this graphically. If you're looking at a value here of a, you plug it into your function and your output must be f of a going into an x square, right? It should be a square. If you have a minus a over here and you're putting that in over here, you're looking at f of minus a. In terms of your output, minus a square is just an a square. So that's why I'm always putting a positive a square. But as you're seeing, we're slowly increasing the difficulty of this function, but the limit procedures are still easy, because what we're seeing is what we're getting. You could do this direct substitution property of limit up to a certain point. Alright, let's look at this question. If you couldn't do this graphing, if you couldn't do it, how would you solve it out? Think back to what I've said, and this perhaps will be one of the biggest tips I'll give you in this video. For the beginning student who's looking into limits, always remember this direct substitution property of limits, DSL. It's my abbreviation, it's not an accurate abbreviation, but I call it direct substitution property of limits. That's a proper term, but the abbreviation is my abbreviation. What it tells you, again, if you have a polynomial or a rational function that's simplified, and you'll never have the instance of a negative in an even root, and you'll never have the instance where you'll have a or whatever polynomial rational function where you'll end up with a 0 in the denominator, then just do this. Put these zeros into places of x and solve it out. I'll get a 0 cubed plus 0 minus 3, and my answer here should be minus 3 in terms of the limit. If someone asks you what the limit value here is, it's just minus 3, because you've used a direct substitution property of limits. Likewise here, you can put whatever a could have been 110, half fraction, or minus 5, minus whatever. You can put a cubed plus 2a square minus 3. If you're looking at a positive a value, you could have done minus a cube plus 2a square minus 3 if you're looking at the minus a plugging in. But again, we're using the direct substitution property of limits. Let's graphically look at what this graph would have looked like. It would, if you were to zero out all of these x's, you have a 0 comma minus 3 y-intercept, and your graph would look something like this. As x approaches this value 0 in terms of the x-axis values, where does your function approach in terms of the y, in terms of the range, in terms of the output? It approaches exactly this y-intercept, -3, and that right there is why your answer is the way it is. As x approaches this hypothetical value a, either from the right or from the left, where does your function approach? Look up onto your curve and then look across it to this y value. Whatever this y value is your answer, and it could have been whatever this numerically would have yielded. If x approaches this minus a value from the left and from the right, where does this function approach in terms of its limit? Look down onto your curve and then look across. Whatever this value is your answer, and that would be numerically determined by actually knowing what that minus a value was. But again, direct substitution property of limits helps you out with these type of questions. A polynomial function, a simplified rational function, just directly input your limit value, and whatever your answer is your answer to your limit question. Now let's break away from those type of questions only for this specific example we'll put out, then we'll come back to those type of question forms. We have this representation here, and we'll do a bunch of questions from this because this will cement many of the topics. If you have this function which is broken as you see it, you have this extension here, this part in the middle, and the rest going over here. You have two vertical asymptotes, minus a and a, and your question was this: find limit as x approaches a, as x approaches this value right here, a. You know this right here would be a comma 0. As x approaches a, remember you look at the right hand and the left hand. When I'm looking at this value as x approaches a from the right, I'm looking at these values of x as they're coming to the right. And what happens? My function proceeds beyond bounds, it exceeds beyond bounds along this vertical asymptote, it shoots up, and my answer is positive infinity. Technically, positive and minus infinity are not good and true limit answers, but they are a conceptual way of you representing something which you cannot truly understand, because we can't truly understand what infinity is, and infinity is not a true limit answer, but we are resorting to using this when we are seeing functions exceed beyond bound, and you have no choice but to present this type of an answer. As x approaches a value from the right, we go upwards towards positive infinity. As this function approaches a from the left, this ends up shooting out of bounds but towards the direction of minus infinity. But this right here is my right hand limit, and this here happens to be my left hand limit, and I told you a limit does not exist if the right hand and the left hand limits are not the same. If someone were to ask you what's the limit for this function, whatever it might be, as x approaches a, your answer should be here, does not exist, d and e. But if someone were to ask you, can you then define this limit in terms of perhaps being a one-sided or a two-sided limit, you could say yes, from the right we'll approach positive infinity and from the left we'll approach minus infinity. But in general, x approaching a will not exist. Let's look right here at this x approaching minus a right here. This right here would be minus a comma 0, x-intercept right over here. If someone were to ask you limit as x approaches minus a, you're seeing a function over here on the top and a function here on the bottom, but they're broken and they're not meeting the same value. You know your answer here will be does not exist, but we'll come to that. We'll look at this minus a as it approaches from the right and x approaches minus a from the left. As x approaches minus a from the right, you just trace your function, it ends right over here. You look across onto your y-axis, your output, your y value, and we see the value is y2. You do the same over here. As x is approaching minus a from the left, we're looking across and we see it's y3. Since the right hand and the left hand limits are again not the same, we must be resorting to saying that the limit does not exist, and that right there is the true answer. As x approaches minus a, the limit does not exist, even though you can make a big argument that from the right it's y2 and from the left is y3. But in general, for this, limit will not exist. Now, if we are looking here at this value b, what if I were to ask you limit as x approaches b? Now, if you're looking at this value b from the right and value b from the left, they'll both land on the same point. Because when you're looking b from the right, it's landing on this point. When you're looking b from the left, it's landing on this point. But remember, as I've told you, your limit answer is what your output is, what your range is, what your y value is. What is your y value at this specific point? It's b comma 0. It's the 0. Whether you're looking at from the right, x approaching b from the right, or you're looking at b approaching from the left, your answer is always 0. And for this instance, x approaches b, this function has a limit and it's 0 because the right hand and the left hand limits are the same. What else can we talk about in this? We can talk about two other things. which are clear. If someone were to ask you limit as x approaches infinity, we're looking here now in the direction, this will go here towards infinity. Where does your function approach? As x approaches infinity, your function obviously approaches this value here, horizontal asymptote, because it's going to trace along this x-axis. In terms of x-axis, the y value is 0. Because x-axis is y equals 0, your function will approach 0. Either you can look at this, supposedly we're right here at infinity, you can look at it from the right and from the left. This y value here will always be whatever that x value is, could be infinity, but the y value will be infinity comma 0, right here, 0. Right hand, left hand. You technically cannot look at right side and left side of infinity because you're out there in the zone of who knows what, because you don't know what infinity looks like, but you know y value there will be 0. So this answer over here, limit of x approaching infinity, will be 0. What about this limit as x approaches minus infinity? This right here is proceeding towards minus infinity. Where does our function approach in terms of that? Well, you're not going to be looking here along the x-axis because it's not grazing the x-axis. There's no horizontal asymptote involved. You look again along here to look at your output. Remember here I looked at my output, except my output ran along the x-axis and I found a y value of 0. Here I'm looking here along the y value and I'm seeing a y value of 3, y3, and that right there is my answer. Limit as x approaches minus infinity, either from the right or from the left, my answer will always be y3. There's no point in looking at right side and left side values here infinity, because infinity is conceptually impossible to understand. So understand everything we've talked about here, and let's get back to our regular survey of questions. Now we have dialed things up a notch again, but look, here I'm not going to be putting positive and minus a. Just assume we're looking at some value a over there, and a in these instances will never equal to 0. We're looking at any value, could be positive or minus, but we're not indicating whether it's positive or minus. Just know that it's not 0, because we're doing it, same questions there. We now have a rational function, polynomial in the numerator, polynomial in the denominator. You could, as I have said, always think about graphing. If you can graph this, you can do it very well. X equals 0 is a 0 of this function. You have a vertical asymptote at x equals 0, which means my y-axis is a asymptote. I have presented a video on rational functions and asymptotes not too recently, but quite a while ago, where I show you how from rational functions you can determine what are the asymptotes, the horizontal, the vertical, the oblique asymptotes, and maybe you could look at that. When you look at this in terms of the horizontal asymptote, a clear horizontal asymptote stands out, and it's y equals 2. If you were to graph this, your graph looks something like this, like that. And we can draw these arrows. If you were to do x is approaching 0, you could clearly see as x is approaching 0 from the right, and x is approaching 0 from the left. We're really going to have a limit which here does not exist, because the right hand, the left hand limits will not be the same. But as x is approaching 0 from the right, this limit is shooting beyond bounds to positive infinities. As we're approaching from the left side, it's shooting downwards beyond bound to minus infinity. Since the right hand, the left hand limits are not the same, the limit does not exist, and that answer must stand. It makes no benefit for you to use a direct substitution property of limits over here, because you cannot directly substitute 0 in places of x. You could in the numerator but not in the denominator, because you'll have a situation of over 0, and that's undefined. Now in this instance where a is not equal to 0, you can directly easily say we'll use a direct substitution property of limits, and I'll just plug the value a, and my limit answer would be 2a plus 1 over a. Whatever a could have been, it could have been 10, it could have been minus 5, but in this instance you'll get a clear numerical value, and that right there will be your limit answer, because here a was not equal to 0. You could clearly substitute this a value and do the direct substitution property of limits and come with your answer. So here your answer would be 2a plus 1 over a, whatever that a value is. We don't know what it is, but it would lead to a good numerical answer, and this question here has been done. And how would you graphically show this? Well, it's not hard. A could very well have been this value. You would look across over here, and you would look here into your y value. This y value would be representative of that. It could have been a minus a right here, and then you would look across here on top and then shoot up towards the y-axis value, and that would be your other limit answer if a happened to be minus. But that's easy. Our problem here for this function is when x approaches 0, we have this discontinuity over here, and limit does not exist. Alright, let's look at this question. Remember, direct substitution property of limits. If you are dealing with a polynomial expression or a rational function, and you can also include radical functions and some trigonometric functions, but we're not talking about that. But generally polynomials and rational functions, there are 4 specific type of functions in which you can very easily employ this. But remember, always simplify your rational function and never utilize it if you're going to be putting a negative into a root where you'll be doing an even root of a negative number, or you'll have a 0 in the denominator. Then do not use this. You have to simplify this rational function. You have x plus 1 whole square in the numerator, you have x plus 1 in the denominator. This cancels out with that. You really just have x plus 1. Something which looked so fancy ended up being no more than a linear equation, y equals x plus 1, going here through 0 comma 1 and minus 1 comma 0. That's all what it was. Now you know you've simplified all of that to this. Very well use the direct substitution property of limits. Put 0 in place of this x and you'll get a value here of 1, and that right there is an answer. And if you had the graph right here, 0. As x values approach this 0 from the left and x approaches this 0 from the right, you look up to your y value output and you know it's 1. Because this coordinate point is 0 comma 1, you look at the y value and that's 1. Likewise here, if a is not equal to 0, and it would not even have mattered a is not equal to 0, because we cannot zero out this denominator, nor can we bring a negative into an even root radical. That situation does not exist. Just put a, whatever it could be, whatever numerical value, fraction, whole number, whatever, integer. Your answer would be a squared plus 2a plus 1 over a plus 1, or just look at it right over here, a plus 1. That would be your limit answer for that. As x approaches a, your function will approach a plus 1, whatever that numerical value is. Let's look at this question. Limit as x approaches 0, we have this cubic function in the numerator and a simple x in the denominator, and limit as x approaches a, and a cannot equal to 0. For that instance, simplify this rational function and then see if you can use a direct substitution property of limits, because that'll make your life so much easy. And this is exactly what you'll get. This cancels out. You'll have x squared plus x plus 1. So suddenly your limit question has become limit as x approaches 0. Use a direct substitution property over here because you're dealing with a polynomial. It's a clear condition where you can use a direct substitution property of limits when you're dealing with a polynomial and a rational function that has been simplified, so long as you don't have a 0 in the denominator and you don't have a negative in an even root radical. You can clearly use this. Plug zeros in places of x, you'll just get 1, and the answer here will be 1. Likewise here, a, you simplified everything to x squared plus x plus 1. Plug a, whatever it could have been, and your answer would be a squared plus a plus 1. Whatever numerically it would turn out to be, that right there is your limit answer to this function question over here. There's no need to even bother graphing it, because you can easily use a direct substitution property of limits for these type of questions and never hesitate to use it. Alright, now things become important and interesting. We have limit as x approaches pi, sine x over pi minus x. You see, now I'm not looking at that x approaching a. We don't need to anymore because our question has changed drastically. We're looking at a rational function, but there's a trigonometric function in here, and we're not looking at as x approaches 0, we're looking at x approaches pi. When you have questions, no matter what form they might have been, generally, you can always go into the habit of just plugging in this pi value, or whatever your a value here is, x approaches a, into your function and see what happens, and see if this specific instance arises where you're getting a 0 over a 0, or you're getting a positive minus infinity or a positive minus infinity, because then you're dealing with an indeterminate limit form. This is a whole different section of limits where you then modify your procedures for solving that limit. But those modifications are not hard, they're very interesting, and they simplify everything. Indeterminate limit form. There are many indeterminate limit forms, but these two are the most important. If you were to put pi in places of these, what would you get? You'll get sine of pi over pi minus pi. You'll get sine of pi, which is a 0, over a 0. You see, I'm getting an indeterminate limit form. But to do these type of questions, then you need to know how to do derivatives. If and when you learn how to do derivatives, then these type of questions become easy, because what would you do here? You would do a L'Hopital's rule. And this is how it's written out, L'Hopital. Some people put an S here, some don't. L'Hopital's rule, where what you end up doing is a derivative of the numerator expression and then a derivative of the denominator expression. And then when you do that, it enables you to plug in exactly what you plugged in before, but this time it may actually help lead you to an answer. When you do the derivative of the numerator, when you learn how to do this, you'll get a cosine x over here. When you do the derivative of this, you'll get a minus 1 over here, and then you can literally plug this pi into places of x. You'll get minus cosine of pi, because this minus 1 can transfer up. You know cosine of pi is a minus 1. Minus 1 hits with this minus and your answer is a positive 1, and the limit answer over here is a positive 1, and it's good. But you see how this procedure required you to know what indeterminate limit forms are, and then it required you to know about this rule, and then it required you to know how to do derivatives, no matter how easy they are. But if you don't know how to do them, you don't know how to do them, and you cannot solve this. But when you have questions like this where you have indeterminate limit forms, you have to be familiar with this type of setup over here, and it's not hard to learn it. You will learn it actually very soon in your class as you're starting out this type of subject. And once you learn it, you might actually end up relying on this technique for most of your questions. Let's look here. Limit as x approaches pi over 2, which you know is 90 degrees, natural log of cosine x. We know generally natural log always goes through 1 comma 0. If you put natural log of 1, you'll get a 0. If you put anything like natural log of 0 or less, you can't do it because it's undefined. If you end up getting a 0 over here, your entire function becomes undefined, because what you can do generally over here for trigonometric function, just see and test this value and put it right here. What are you doing? Natural log of cosine of 90. You know cosine of 90 is a 0. You're doing natural log of 0, and you know if you take your scientific calculator and you do a 0 and you natural log it, see 0 and natural log, you get undefined, you get an error. You cannot do it. You cannot do it. So what do you end up saying over here? Your limit does not exist. So this is one of those rare instances where something easy is a blessing because your calculator helps you through it. Let's look at this question. Limit as x approaches infinity 5 minus x over x plus 5. It's a rational function. It doesn't help to use the direct substitution property of limits because you can't substitute and put infinity. We don't know what infinity is. When you're looking at this rational function, you should be thinking about asymptotes because you can't simplify this at all. If you do the 0 of the denominator, minus 5 plus 5 minus 5, and x equals minus 5, value zeros out your denominator, and that's a good vertical asymptote. If you were to do a horizontal asymptote determination, I'll put a link for a video where you can learn how to do all of this. You can get a good horizontal asymptote by a good procedure where you divide the numerator and the denominator by the highest order expression of your variable in terms of an exponent. I only have x to the power of 1. If you divide everything by that, I'll get 5 over x minus 1 over x, which is just a 1. I'm just splitting everything into their individual denominators. I'll get 1 plus 5 over x. Limit as x approaches infinity, these zero out because you're dividing 5 by such an increasingly large number, it zeroes out. You get a minus 1 over 1, which is a minus 1, and that is a horizontal asymptote. That y equals minus 1 is a horizontal asymptote. And that's how I've determined this. And I know my graph is going to look something like this and something like this. Limit as x approaches infinity, as x values approach infinity in the direction of positive infinity. Where is my function approaching? It's approaching this asymptote right over here, minus 1, and minus 1 will be my answer. If you couldn't do any of this graphic procedure, how could you actually solve this out? You can do this by means of limit approximations. Come up with a value which is close to infinity, the value you're looking at. How about just do like a value this large, and you plug this value right here into your calculator and see what happens. We could even have used something like this: 1 times 10 to the power of 9. Plug 1 times 10 to the power of 9 over here and into your function, and we'll do it in the denominator and we'll work upwards. 1 exponent 9 plus 5. This is my denominator expression. I save that. Then I do 5 minus 1 exponent 9. I divide that by my saved value, and what am I going to get? Minus 0.99999, which is very close to a minus 1. The more zeros you add, the more closer you'll get to minus 1, but minus 1 is a good answer. When you have questions like this, rational functions, and you don't know how to do asymptote determinations and graphic procedures, then use limit approximations. And the technique for limit approximations is this: you find a value on the right hand and the left hand of the value you're looking at, and you plug that in. Since I was looking at infinity, a good value, well, you cannot have a good value because we don't know what infinity is. Let's say x here was approaching here a, and here a was equal to 1, so x was approaching 1. A good right hand value you could have used for something to the right of 1 would be 1.00001. A good left hand value to the left of 1 would have been 0.99999. The closer you are to that true value, the more accurate will be your limit determination. You plug these values into places of x of your rational function and it'll give you exactly what you want. This right here is called the limit approximation technique, and it's a surefire technique for doing limits. I don't do this too much because direct substitution property of limits helps you out greatly. The L'Hopital's rule helps you out greatly, and doing rational functions by this graphic procedure, it's not like you're cheating. If you know how to do the graph and the asymptote determination, you can do that on your side. You're not cheating. You're reading off your graph and it gives you your value, and that right there is good enough. Let's look at this question, an interesting question, but requiring you to know the L'Hopital's rule. Think about it. You cannot use a direct substitution property over here. It would be difficult to do limit approximations where you're looking at some value that you could technically just do 1 times 10 to the 9 or 10 to the 90 or 99, but you'd be limited severely by what your calculator can do for you. How about you just plug infinity in places of x? What do you get? E to the infinity over e to the infinity plus 1. What are you really getting? Infinity over infinity plus 1, which is what? Infinity over infinity. And now we're looking at that indeterminate limit form I was talking about, for which you have to use a L'Hopital's rule. I abbreviate that as LH. You do the derivative of the numerator, you do the derivative of the denominator, and then it enables you to work your function. When you do the derivative of e to the x, you learn it's just e to the x. When you do the derivative of e to the x plus 1, you learn again it's just e to the x. And now you can literally put infinity into your answer in places of x, but you don't need to. Anything divided by the same thing is always equal to 1, and putting in the infinity is useless. Your answer is just 1, and the answer to this limit is 1. And it was so easy because we recognized we have an indeterminate form. You have to know this word, indeterminate limit form. It's a big nasty word, this indeterminate limit form, but once you know and identify what your indeterminate limit forms are, you can use this rule and it'll greatly simplify your life. The most important indeterminate limit forms are 0 or and plus and minus infinity divided by plus and minus infinity. There are a bunch of other ones, we won't talk about that, but I've posted 2 videos on indeterminate limit forms and how you handle those. They're lengthy videos, but they're necessary because this is something you will likely see in calculus. Look at this, and this is our second last question. We'll do one more after this and we'll call it with the video. We have limit as x approaches infinity. We have this rational function. There's no point in simplifying this rational function because you cannot simplify it much at all, and you're dealing here with an a value which is infinity. Very difficult to even substitute and do the direct substitution property of limits. If hypothetically you were to put infinity in places of these x's, you will have 2 to the power of infinity square minus infinity over 5 to the power of infinity square plus 1. All of this conceptual nonsense going on over here. You're technically really having infinity over infinity. You have that indeterminate limit form at play, and you can just use the L'Hopital's rule. You do the derivative of the numerator and you do the derivative of the denominator expression. Once you learn how to do derivatives, you know that's 4x minus 1. And here you'll have 10x. And when you put infinity over here, what do you see happen? You still have infinity over infinity plaguing you. You cannot do anything. The beauty of the L'Hopital's rule procedure is so long as these indeterminate limit forms exist, you can keep repeating the procedure until you've exhausted these forms and you come back to nice clean forms. If I did the derivative here again of the numerator and the derivative here again of the denominator, 4x minus 1 will just break down into a 4 in terms of its derivative. This will just break down into a 10 in terms of its derivative. 2 or 5. That right there is my answer. So this answer, this question over here has a limit as x approaches infinity. This rational function will approach 2 or 5. If you were to graph it somewhere along the value of infinity and you would look up onto your curve and you'd look across into your y-axis, you'd land on 2 or 5, and that right there is why the answer is the way it is. If there is a chance for you over here to handle this type of question, you don't know how to use L'Hopital's rule procedure, let me show you this accessory technique. It is this. When you have a rational function with these type of polynomials in the numerator and denominator, divide each of those with the highest order exponent variable that you see. I'm just writing it out in this form. I'm dividing the numerator with the highest order variable exponent and the denominator by the same highest order variable exponent. I have an x squared and an x. The highest order variable in terms of exponent is an x squared. Divide both and simplify. You'll have 2x squared over x squared minus x over x squared all over 5x squared over x squared plus 1 over x squared. Simplify where you can. I have the x squares cancel out here. I have a 2 minus 1 over x right? X divided by x squared is 1 over x. I have a 5 plus 1 over x squared. Now look carefully here. As x approaches infinity, I put infinity in places of x. I'll do 1 divided by infinity, it's going to be 0. 1 divided by infinity, it's 0. Think about it. 1 divided by an increasingly large number, you'll have 0.00, who knows how many zeros, then you'll have some numerical constant. All of this is equal to 0. You essentially have 2 over 5 come out, and that right there is this. And we did this without the L'Hopital's rule procedure. You can use this and get away with it sometimes, but this right here is a more universal approach. Again, this technique over here for a rational function with this presentation such as this, divide the numerator and the denominator expression by the highest order exponent in terms of variable, and maybe you can get away with something like this and come to a clean answer. With regards to the same question, we can boost your confidence some more and tell you that you can do this also by limit approximation. As x is approaching infinity, a conceptually very large number, you could even roll with just 1 times 10 to the power of 9. You wouldn't have to look at a right side or a left side number along the infinity. This number alone would very well suffice. Take this 1 exponent 9 and plug it everywhere in places of x. You would have 2 times 1 times 10 to the 9 square minus 1 times 10 to the power of 9. I'm just plugging this number right here into places of x, and you know scientific calculators can easily handle something of this magnitude. Is nothing out of the ordinary. And if you were to take this expression over here and just run it through, you would of course work with the denominator, save that value, then work in the numerator and bring your memory recall. We can do this 5 times 1 exponent 9 square plus 1. I get this 5 times 10 to the 18. I'll save that. Then I work with the numerator. 2 times 1 exponent 9 square minus 1 exponent 9. I divide that by memory recall. I get 0.3999. And you know we're seeing a large value here in terms of these repeats, large repeats, 0.3999. We've already determined the expression over here in terms of its limit is equal to 2 or 5, which you know is a 0.4. But this right here is eerily close to it, and the technique of limit approximation works just as well. You could have done this via L'Hopital's rule. You could have used it via that intermediate technique where you simplify this by dividing the numerator and the denominator by that highest order exponent variable we had was x squared, right? And then you can do it by limit approximation. So there are 3 ways where you can do this, and it's not too hard. Keep this technique in your mind. You can generally use this technique for any question generally. Your fail-safe technique right over here. Last question over here. We'll look at both of these scenarios. Remember this here, a is not equal to 0, but a can be positive or minus, alright? It can be positive or minus values. You know 1 over x is what? What is 1 over x? It's a graph of something like this, a hyperbola, right? Limit as x approaches 0, 1 over x. You know you always have to look at the right hand, the left hand. As x values approach 0 from the right, your curve shoots up towards the direction of positive infinity. Limit as x approaches 0 values from the left, your curve shoots down here towards the minus infinity. Limit as x approaches 0 in general does not exist because the right hand and the left hand limits are not equal, therefore the limit cannot exist. That right there would be your answer. If someone were to ask you just this as a question for this, as x approaches 0 from the right, then you can present an answer. Your answer is positive infinity. If someone were to ask you x approaching 0 from the left, you can say minus infinity, and that right there is acceptable answer. But if your question is x approaches 0, there's no designation of right or left, then your answer must be does not exist, because you evaluated the limit from both sides at 0, and your limit right side and left side are not the same, so this has to be your answer. Same function now as x approaches a from the right and the left. We're not looking at 0 anymore. A could technically be any value. This here could be a, this here could be minus a. You look up over here onto your curve, you look across, whatever that value is your answer. So in this instance you could have 1 over a. In this instance you look across, and across over here your answer could be minus 1 over a. So both of these answers are good. You just don't know what a is. If x is approaching 10, your answer is 1 over 10. If x is approaching minus 20, your answer is minus 1 over 20. In that instance it's easy. You can always get the left hand and the right hand limit for both of these values of a, so long as a is not equal to 0, because here your function is continuous. There's no break in it. Your break only arrived here at 0, which was very well your vertical asymptote. Your vertical asymptote was x equals 0. Remember 1 over x, you can zero it out by putting a 0. zeroing it out, this rational function gave you your vertical asymptote of x equals 0, and you actually also have a horizontal asymptote of y equals 0. I would strongly encourage anyone to look at that rational function asymptote video, because this, when I'm looking at this, I'm seeing two asymptotes. One is y equals 0, which is my horizontal asymptote, and one is x equals 0, which is my vertical asymptote, and that's how the graph is. You have an asymptote here, you have an asymptote here, and your function is split up across those two asymptotes, hence the hyperbola that it is. So keep everything I've talked about in this video, and this right here should be a good introduction or a good conceptual understanding for what a limit is. I've talked about a lot in this video, so you might have to look at it maybe once or twice, but it's nothing too hard. It can become very hard as you progress beyond this subject over here, but if you don't have this basic understanding and you go to the next more difficult form of limits, like those indeterminate forms, then it becomes really nuisance and frustrating for any student. So look at this video and see if you can take anything out of it. Thank you for watching. Have a nice day.